So now this is a revision of what you have done in your previous thermodynamics, basic thermodynamics. So before we goes into vapor power cycles, it is better for us to know all about, or at least a bit about, the formation of steam. Okay. Now the temperature at which water starts boiling depends on the pressure. Okay. So it's just like, for example, if you are boiling water in the kitchen, okay, it is subjected to atmospheric pressure. The surrounding pressure plays a very important role. So when the surrounding pressure changes, actually your boiling temperature of the H2O or the liquid or water will change as well. So when you fix the pressure, the boiling temperature of water, okay, if let's say the surrounding pressure, let's say it is at the atmospheric pressure of 1.01325 bar, then the boiling temperature of water or H2O liquid will be at 100 degrees C at 1 atmosphere. So in this section here, okay, I will be basically explaining to you from the changes of phase from water to steam. Now, the temperature at which water starts boiling depends on the pressure. Therefore, if the pressure is fixed, then the boiling temperature will also be fixed. We say boiling temperature. Okay, so water will boil at 100 degrees C at 1 atmospheric. That is equals to 1.01325 bar or 101.325 kPa. Okay, so let's say we have a cylinder, okay, with a piston. So let's say we place a weight on top of the piston so that the pressure that is exerted on the system or the liquid below, it is standard or fixed at 1 atmosphere. 1 atmosphere. So let's say initially the temperature of the water is 20 degrees C. Then when you supply heat to the water, what happened is the temperature initially, okay, at constant pressure throughout, yeah, we are looking at constant pressure at constant 1 atmospheric pressure throughout the process, the entire process. Initially temperature is 20. So when heat is supplied, the temperature will start to change. Okay, the temperature will start to change from A to state point B. The pressure still remain the same, but the temperature will increase until it reaches 100 degrees C. So at this 100 degrees C at the beginning, you can see bubbles formations starts to take place. Bubble formation start to take place. And we say the water is boiling. So at that instant, we call it as saturated liquid. Saturated liquid. So the water that you took initially is called compressed liquid. Then when the water start to boil, is called saturated liquid. So the word saturated or saturation here means the liquid is unable to accept or to absorb even though a little amount of heat at constant pressure. What happens is if it absorbs, even though it's a very minute, very small amount of heat, it will undergo a change in phase. It will undergo a change in phase from liquid to vapor. If it is for water, then we call steam. Okay, we call it as steam. So water will start to change its phase from liquid to steam by, okay, stages by stages, okay, and then when more heat is applied at constant pressure, If more heat is applied at constant pressure, what happens to this boiling liquid or saturated liquid is it is undergoing a changes in phase. So it will move from state point B to another new state point C, which we have a mixture of saturated vapor and saturated liquid. That means we have a mixture of steam with liquid. But you have to take note, the temperature here remain constant while the phase of the substance changing, okay, by stages into vapor, So during this process, the heat that is applied in order to change the phase of the substance is called the latent heat of vaporization. The latent heat of vaporization. Or the other way around, that means when vapor change back to liquid, we call it as condensation. Okay? So from this, you can see, okay, partially or a part of the water or the boiling liquid earlier has been converted to vapor or steam. Okay, so if let's say more heat is applied at constant pressure, let's say more heat is applied at constant pressure, okay, what happens is further changes will take place. That means more liquid changing to vapor. So it comes to a stage D, where the pressure still remains constant, the temperature still remains constant until every single drop of water has been changed to steam, And at this stage, we call it as saturated vapor. It means that even though a slight amount of heat added or removed, we say remove, even though a slight amount of heat removed, okay, that means cooling, what happens is the vapor will start changing back to liquid. So saturated vapor, the word saturation or saturated here means is already to the limit. Okay, so you cannot take away, even though an infinite, a very small amount of heat, it will undergo changes and condensation will take place like that. So what happens if, let's say, I supply more heat to this, okay, constant pressure? So the temperature now will not remain at 100 at this stage where every single drop of liquid has been converted to vapor. So at this stage here, if let's say we supply more heat at constant pressure, this now will undergo a change in temperature. Okay, will undergo a change in temperature. Okay, maybe to 120, maybe to 101, or maybe to any other temperature higher than its boiling temperature or its saturation temperature. Now, when you look at this stage here, B, C, and D, you can see at these three different stages, okay, the temperature remain constant here. And this temperature, we call them as the saturation temperature. The saturation temperature. Okay, so this saturation temperature will not change until the changes in phase of the substance has complete. Okay, then if let's say more heat supply, then the temperature will increase. After that, will increase further on until we call the system or the substance now is categorized as superheated, and we call it as a superheated vapor or superheated steam. Okay, so based on this, we have compressed liquid. Sometimes it's even called subcooled liquid. So I will define each of these terms here. So a substance that is a substance that it is not about to vaporize. Okay, so any liquid or any water that you took from your house, from the tap, is called compressed liquid. Okay, it's called the compressed liquid. Then you have saturated liquid, a liquid that is about to vaporize. It's about to vaporize, or we can call it as the boiling liquid. Excuse me, boiling liquid. Then you have saturated vapor, or we can call it as dry saturated steam or dry saturated vapor sometimes. Okay, a vapor that is about to condense. So if let's say a little amount or a slight amount of heat removed, what it happens is it will undergo condensation. Then saturated liquid vapor mixture is this. Okay, the state at which the liquid and vapor phases coexist in equilibrium. Okay, so sometimes we call it as wet vapor. So when we are dealing with saturated liquid vapor mixture or wet vapor, we have a term called the dryness fraction. The dryness fraction is actually defined as, okay, the mass of dry steam formed divided by the mass per kg, divided by per kg of mixture. Okay, that dry steam, kg of dry steam per kg of mixture. That is dryness fraction. Is actually measuring the percentage of dry steam that is in the mixture. Okay, then superheated steam or superheated vapor. Now, when we say superheated vapor, that means we can be referring to H2O, or we can be referring to some other gases, or some other, most of the time, refrigerants. That means the cooling agents for refrigerators and aircon. Okay, so anything that is in the form of gas, we call them as vapor, and which is able to convert back to liquid, we call it as vapor. Okay, so for H2O, okay, we call it as steam. So that is why sometimes you call it a superheated vapor or superheated steam. So that is a vapor that is not about to condense. Okay, so you must be able to identify what is saturated liquid, saturated vapor, wet vapor, and superheated vapor. So we will be going about, we will be going into this, okay, in the TS or PV diagram in the later stage. Okay, the next slide. So that is dryness fraction, which we call it as the quality of the steam, or sometimes we call it as dryness fraction. Most of the time nowadays, we call it as the quality, but previously we called it as dryness fraction. So that is the ratio of mass of vapor, the mass of dry steam, to the total mass of the mixture per kg of mixture. So the quality of the steam, that means the dryness fraction, that means the X, can vary from 0 to 1. So here in this stage here, you can see my cursor, yeah? Saturated liquid, the X will be 0. Dry saturated vapor or dry saturated steam or saturated vapor, X will be equals to 1. X will be equals to 1 here, X will be equals to 0 here. So from here to here, the X will vary from 0 to 0.01 until it reaches 0.099999 until it reaches 1 here. So superheated steam, we don't have dryness fraction. We don't measure the quality of the steam for superheated steam and for compressed liquid. So usually X is 0 here, X is 1 here. So in between, X can vary from 0.0001 to 0.999999 until it reaches 1. Okay, so after that, okay, we don't measure X. So the properties of the saturated liquid are the same whether it exists alone or in a mixture with saturated vapor. So for any compressed liquid, okay, for any compressed liquid, we also don't measure the X. For saturated liquid, remember X is equals to 0 because there is no dry steam or dry vapor or saturated vapor that exists in this phase. Okay. So now, this is your PV diagram. So what we have just now, okay, A, compressed liquid. Now we are looking at a constant pressure, constant 1 atmosphere. So on this diagram here, this red dome here, D-O-M-E, is known as the saturation dome. Saturation dome. How these domes were obtained? Actually, it was plotted based on number of points within or along this line here. Number of points which is based on different pressure. Okay, at different pressure, okay, the liquid will boil at a different temperature. At different pressure, the liquid will boil at a different temperature. So at this point B here, let's say this is 1 atmosphere. We say now this is called the isothermal line. This blue line is called the isothermal line. This red color, red dome here is called the saturation dome. Okay, so this point B here is where is your saturated liquid, and this point D is where you have your saturated vapor. So that means at this point X is 0, dryness fraction is 0, and at this point here dryness fraction is 1. So at this point here A is where you have your compressed liquid or subcooled liquid. At point B here is where you have your saturated liquid. At any point along between B and D, at any point between B and D is where you have your wet vapor. Okay, wet vapor, which is the mixture of liquid and dry vapor. And then point D is where you have your saturated vapor or dry steam. And then point E is where you have your superheated steam. Okay, superheated steam or superheated vapor. So you can see basically the temperature here on this blue line here, okay, at this pressure 1 atmosphere, okay, any point, if you place any point on this line here, the temperature will be the same at 100 degrees C. Okay, and then if let's say you move vertically upwards or downwards, then the temperature and the pressure varies. So you will have a series of you have a series of isothermal lines, okay, and you have a series of these points here will appear, and a series of these points here, that is your saturated vapor points, will appear along this line, and saturated liquid points will occur along this line. So if you were to plot, okay, if you were to join all the points together, actually it will form a line and a curve like this, showing you the different boiling temperature, that means different isothermal line, okay, at different pressure. Okay, so this line is called the saturated liquid line. And most of the time when it refers to your properties of thermodynamics, let's say exclude pressure and temperature. Let's say when you look at specific volume, when you look at specific internal energy or internal energy, when you refer to specific enthalpy, when you refer to entropy, or even the specific capacity constant pressure, you see a subscript F. Okay, the subscript F actually refers to saturated liquid. This condition of the substance is what we call in the saturated liquid form. Then when you see anything with the subscript of G, that means you have Vg, Ug, Hg, Sg. Now we say that the substance is in this condition, that means dry saturated. This line here we call dry saturated vapor line. This line we call saturated liquid line. Okay, these are isothermal lines. Okay, you have a series of temperature line which we call isothermal line, which you can see is slanting down, but then actually is slightly curving, yeah, and then become horizontal. Why is horizontal in between here? because here at this moment, no temperature change. All the heat that is applied to the substance is used to change the phase of the substance. So that is why it remains constant horizontal. And then it will start to slide downwards. Okay? So we call them as isothermal lines. And then your pressure line, of course, across horizontally, crossing the graph. Okay, this is called the saturation dome. Anything inside here, inside the dome, is called wet condition. Okay, wet condition, which is having a mixture of vapor and liquid with a varying of x. That means x can be varying from 0 to 1 from here. And then outer region here, at this part here, is called superheated. And then around this part here is called the compressed liquid. And here, remember, is wet. And then on this line is the saturated liquid or boiling. And then on this line here is called the saturated vapor. Okay, saturation temperature. So you have saturation temperature T with a subscript of S when you refer to most of your property tables, even in Yunus and Schengel or in McConkey's or by this UK standards property tables, which I can't recall, sorry, now, because I got a sample to show you afterward. So T saturated, so usually is written as T with a subscript of S. Okay, the temperature at which pure substance changes phase at the given pressure. So at a given constant pressure, okay, any changes in phase, the temperature at that stage, at that particular instant, is called the saturation temperature. So these are called saturation temperature. So the temperature at this instant is called TS. It's called the saturation temperature. And saturation pressure is the pressure at which a pure substance changes in phase. So when anything undergoing changes in phase, okay, the temperature or the pressure at that particular instance is called the saturation temperature and the saturation pressure. So remember, during this period, during this instant, this period of time, the heat that is supplied is called the latent heat of vaporization. It's called the latent heat of vaporization. All the heat that is supplied to the substance is used in changing the substance, in breaking the intermolecular bonding between the particles or the molecules of H2O. So latent heat, the amount of energy absorbed or released, okay, absorbed to change liquid to vapor is called vaporization. To change vapor back to liquid is called condensation. Okay, the amount of energy absorbed or released during a phase change process. Then latent heat of fusion is the amount of energy absorbed during melting. That means ice changing to water or water changing back to ice. Okay, so the heat that is supplied is called the latent heat of fusion. It is equivalent to the amount of energy released during freezing. Freezing, that means solidification. Solidification, that means changing from liquid back to solid. Freezing is especially also used, the term that is used for liquid changing back to solid. For example, water changing back to ice. So solid stage, we have ice. Liquid stage, we have water. Vapor stage, we have steam. Okay. So latent heat of vaporization or condensation, that is the amount of energy absorbed during vaporization, and it is also equivalent to the energy released during condensation. Okay. So the magnitudes of the latent heats depend on the temperature or pressure at which the phase change occurs. Okay. At 1 atmospheric pressure, the latent heat of fusion of water is 333.7 kilojoules per kg, and the latent heat of vaporization is at 2256.5 kilojoules per kg. These are extra okay, knowledge that these are the things that you should know. Okay, at 1 atmospheric, what is the latent heat of fusion, how much, and what is the latent heat of vaporization, which is standard at 1 atmospheric. And then the boiling temperature of water is for water, yeah, for water. Okay, the boiling temperature of water is 100. Okay, the atmospheric pressure and thus the boiling temperature of water decreases with elevation. Decreases with elevation means now from one place, that means under the hill, and then when you travel up the hill or when you travel up a mountain, as you go higher, the pressure will be lower. The more you go, higher you go, the lower will be the pressure, and as well as the boiling temperature of water. So when you're at home, when you are boiling water, maybe it's at 100 degrees C. But then when you go up to a place which is higher, maybe 100 miles away from your house, which where you go, you travel up the mountain. So when you're at the mountain top, at the hilltop, okay, the boiling temperature will not remain at 100. It will definitely be lower or lesser than 100 degrees C, because the pressure is lower. The surrounding pressure is lower. So the boiling temperature also will be lower. Please remember that. So the pressure actually varies with elevation, that means with height. Okay. So the boiling temperature also varies with respect to height. Not temperature. What I mean is the boiling temperature. Now, point A is where you have your compressed liquid or subcooled liquid. From the previous diagram, we can transfer it to this TS diagram, to this PV diagram. This is a PV, okay? Then you have point B, which is this, is the saturated liquid or the boiling liquid. Usually bubble formation start to take place. Then point C, or any points between point B and D, we call them as wet vapor or mixture of vapor and liquid. This is when the term X is being introduced, and it is being referred to as the ratio of mass of dry saturated vapor to the total mixture. And then point D is where you have your dry saturated steam. Usually X here is equals to 1, and on saturated liquid, usually X equals to 0 here. So point E at this region here, in this region, is called the superheated steam or the dry steam further heated at constant pressure. So in this diagram, okay, I have basically shown you the area of which in your PV or TS or pH or HS, okay, you always refer to the left-handmost from the saturated liquid line. All these various property diagrams, they do have a saturation dome, but their saturation dome different from one another. Okay, so you can go online to view the various shape or pattern of the saturation dome based on different properties, okay, of property diagrams. So to the left-handmost of your saturated liquid is always called the compressed liquid, and usually the properties on the saturated liquid line, any of these which is on the saturated liquid line, is always given a subscript F like this. So any volume or any internal energy or any enthalpy or any entropy which is equals to the value of volume with a subscript of F, with the internal energy with a subscript of F, enthalpy with a subscript of F, or entropy with a subscript of F, we call them as saturated liquid. Okay, so if let's say any given volume, internal energy, enthalpy, or entropy is less than the dry saturated vapor properties, that means the Vg, the Ug, and the Sg. So any properties of thermodynamics that lies on this line here will be given a subscript of G, representing that it is a dry saturated vapor or dry saturated steam. So any values given less than the G, okay, will be considered as wet vapor. In between, okay, usually we compare with the G values. I usually call it as G values, properties with a subscript G. Okay, properties with the subscript G. Okay, any volume, internal energy, or entropy or enthalpy that is given, which is less than, when you compare, when you refer to the table, it is always categorized as the mixture of liquid and vapor or wet vapor. So at this moment, what you need to do is you need to find out the dryness fraction. The dryness fraction will be here in the UFG here. There should be an X here beside the UFG. And then X beside the HFG and X beside the SFG. All the X is missing already. X here, and the X here. Okay? So you will have the X UFG, X HFG, and X SFG. Okay, that is the dryness fraction. You can make use of this to find out the dryness fraction. So any values that is given which is equals to the G values, we call them as dry saturated. Anything that is greater than the G values is called the superheated. So the superheated usually lies in this region here. Okay. So this is a sample of your table. A sample of your steam table. Now, let's say at this temperature. Okay. Now, any temperature shown here will be the saturation temperature with respect to the saturation, the pressure, and the temperature. Okay, so you will see most of the time T with a subscript S, P with a subscript S. That means it is referring to the saturation temperature and the saturation pressure. So at this pressure, we say the water will boil at this temperature. At this pressure, the water will boil at this pressure. So this is Vg. You can see the subscript G here. So this subscript G means here, okay, the saturated for dry saturated vapor. For dry saturated vapor, I use the term dry saturated. Listen very carefully because we have the subscript G here. The dry saturated vapor or the specific volume of the dry saturated vapor at this pressure, at this temperature is equals to 192.6 meter cube per kg. So if let's say when you are solving problems, when the question gives you at this pressure and at this temperature, at this pressure and at this temperature, if let's say the question gives you a volume of let's say 180 meter cube per kg at this pressure and this temperature, then we say the condition of the substance is in the category of wet vapor. That means in the category of mixture of liquid and vapor. So at this stage, you have to know what is the dryness fraction. Okay, if any given value of V is less than this, let's say I give you 180, or let's say I give you 200, let's say I give you 200, which is more than this Vg, then the steam will be superheated. Or if I give you 192.6 at this pressure and this temperature, then the steam the steam will be dry saturated, or the substance will be dry saturated. Less is wet, equal is dry, more than is superheat. Remember, less than the G value, okay, if you take Vg to compare, less than the G value is wet, equal is dry, more than is superheat. That is how I usually categorize things. Okay, and then if it is equals to the F, then it's saturated liquid. Then you compare the Hg. So the dry saturated vapor, dry saturated because we've got the G here. This one is called saturated liquid, enthalpy of saturated liquid, okay, at pressure and temperature, saturated liquid, enthalpy of saturated liquid, enthalpy of dry saturated. So any H I give, if it is equals to this, then it's dry. Any H that I give you or in a problem or is given to you less than, that means it's wet. One is wet, you have to find out the dryness fraction. If it is more than, then it's superheat. The same for entropy as well. If it is equals to this, then it's saturated liquid. If it is less than this, but more than this, always we take the G as comparison, okay? So anything less than this is liquid. Oh, sorry, mixture or wet vapor. Anything equals is dry. Anything more than is superheat. So if let's say, for example, I refers to the next table, let's say at atmospheric pressure, okay, at atmospheric pressure, 1 atmospheric or 1.01325 bar. The boiling temperature is 100. So the Vg will be 1.673. Any volume given less than this value, that means the steam is, or the substance is wet. Anything equal, dry. Anything more than is superheat. Or the enthalpy you can find out. Okay? The enthalpy, Hg, and the entropy, Sg. So in this is slightly different, but then it's from the same table also. I will provide you with this table. So these are called the saturation pressure. As you can take note, whenever the pressure change, the boiling temperature or the saturation temperature also will change as well. So this is called specific volume, dry saturated. This is internal energy of saturated liquid, internal energy of dry saturated, enthalpy of saturated liquid. This is mixture. Now how you get, now here you don't have UFG. Here you can see there is HFG. Okay, if let's say I want to get UFG, then you need to take this value, UG minus UF to get UFG. It's just like when you look at this, HFG is actually 2514 minus 29. So you get this 2485. So the same here, 8.974 minus this, you get your SFG. Okay. So this part is the superheated for the superheated. So you can see the temperature in this row, the pressure varying in this column. So in this column here, you can see all these are the saturated properties, the dry saturated properties. So at pressure 5 bar, the water will boil at this temperature. At pressure 5 bar, water will boil at this temperature. Okay, and then the volume will be this, internal energy will be this, enthalpy, entropy will be this for if dry saturated. If let's say you got something that is more than, then you have to see, let's say, example, this is Vg. So you can see this volume is more than your Vg. So that means this condition here is superheated. So you can refer, okay, so this temperature is 200 and the pressure is 5 bar. When the steam is superheated from 5 bar, steam at 5 bar is superheated to temperature 200, then the specific volume is this, internal energy, enthalpy, entropy. At 5 bar, if it is superheated at 250, then the volume, internal energy, enthalpy, entropy here. Okay? Now, when you look at this, okay, so you can see this is 80 bar. Then they give you the volume, the Vg, the Hg, and the Sg. The U is not given, so how are you going to find the U? So remember, you have to use this formula, H equals to U plus P V. Okay, so let's say at 80 bar, because this is very high pressure, so they don't give you the internal energy. So the internal energy can be found by using H minus PV. So your H in kilo, pressure in bar, so you must 10 times 10 power 2, and then your volume. So the volume they have given you, V equals to 10 to the power of negative 2. So remember, if let's say I take this part here, for example, where I have V over, sorry, I'm not using pen. I'm not using pen. So my pen is out of order. So you have V over 10 to the power of negative 2 is equals to 2.994. Okay, so your volume based on this will be equals to actually 2.994 times 10 power -2. Okay, so this is basically a revise for what you have, most of you which have done thermodynamics earlier, which maybe you have forgotten. So this, I hope it will help a lot, okay, in getting to know what is going to happen in the rest of the chapters. Okay, thank you. Thanks everyone. Stay safe.